Hope this video lifts or elevates your spirits.
So first, let's talk about a person who walks into an elevator that is at rest on the first floor, and then that elevator takes the person up to a floor above the first floor and stops, letting them get out there. I am going to draw a free body diagram of the person inside the elevator at each point that the elevator, and thus the person, changes its motion. So I'm going to draw the person as a box because when we draw free body diagrams, we draw everything as a box. At the beginning, the elevator is at rest, and so the person is also at rest. There's no change in speed or direction, so the acceleration of the person is 0. So let's take a look at what forces are acting on this person. The person is on Earth, so there is the force of gravity downwards, and in order to keep the person from falling through the elevator floor, the floor pushes up on the person with the normal force, and the normal force is equal to the force of gravity to make the net force equal to 0. And this is all happening at t0 at the beginning. The length of the arrow for the normal force is equal to the length of the arrow of the force of gravity because those two forces are equal in magnitude in order to make the net force equal to 0 because the person is not accelerating. Alright, then the elevator takes off in the upwards direction. By the way, I'm going to call upwards positive for this problem. So the person is moving upwards with the elevator. The person does have some speed because the elevator is going upwards. Now, because the person started from rest and now acquired a certain speed, there is an acceleration. The person is accelerating in the upwards direction. The speed is increasing and the acceleration is positive. The person is still on Earth. Their mass has not changed. So the force of gravity is still the exact same. However, in order to make the person accelerate in the upwards direction, there must be a net force in the upwards direction. So the normal force must become greater than the force of gravity in order to cause that upwards acceleration. So the floor is now pushing much harder on the person than the force of gravity is pulling down, and that's what allows the person to accelerate upwards in the elevator. At some point, the elevator reaches a constant speed, and so the person inside the elevator also reaches a constant speed. Still on Earth, force of gravity has not changed. Now, the elevator and the person inside of it are moving at a constant speed. So V equals constant. And so if we are moving at a constant speed, the acceleration is 0. We're not changing direction and we're not changing speed. So what does that mean? Well, that means that the normal force must be equal to the force of gravity so that the net force equals 0. So what's interesting here is that this free body diagram looks exactly like the free body diagram that we drew at the beginning. And so from this free body diagram, you actually cannot tell whether the elevator is at rest or if it's moving at a constant speed, because in both cases, the net force equals 0. At T4, the elevator is now going to slow down to a stop. So what that means is that the person inside the elevator, their speed is decreasing. It's going down because it's slowing down to a stop, which means that the acceleration is negative. So if the elevator was originally moving upwards, in order to slow it down, there must be a net force in the downwards direction to take away some of that speed. And because that net force is going to be in the downwards direction, that is why our acceleration is negative, because we said downwards is negative and the direction of the net force is the same direction as the acceleration. So if the net force is downwards, the acceleration is downwards and thus negative. So the force of gravity still has not changed on the person. However, The force of gravity arrow now needs to be longer than the normal force arrow so that there's a net force in the downwards direction. So the normal force here is actually really small. It's smaller than the force of gravity. So the floor actually has to push up less on the person than the person's weight so that that person will slow down to a stop with the elevator. And finally, at the end, at T5, the elevator and the person inside of it are at rest. The speed is 0, the acceleration is 0. Force of gravity downwards, and because we are not accelerating, the magnitude of the normal force is equal to the magnitude of the force of gravity, so that to make the net force equal to 0. 0 acceleration, 0 net force. When you're standing in an elevator, you feel the floor pushing up on you. When the elevator is at rest or going at a constant speed, the floor is pushing up on you with a force equal to your own weight, so you feel like your normal weight. However, at the beginning, when the elevator first accelerated and got up to speed,
you feel squished because the floor of the elevator has to push up on you more than your own weight, so you feel squished.
So in the middle, when you're moving at a constant speed, all of you is moving up at a constant speed, and when the elevator starts slowing down, because of inertia, your body still wants to keep going up, and so that's why your stomach might feel kind of funny right before the elevator comes to a stop at the top. Once the person inside the elevator gets up to speed, you don't need any extra force to keep that person moving up because of Newton's first law and because of inertia, and so the net force is 0. That is why the elevator floor does not have to push up on you any harder while it is moving at a constant speed. Okay, so now let's talk about standing on a scale inside the elevator. Find the reading on a scale in an elevator. What are you really looking for? So if you are standing on a scale in an elevator, the scale is the thing that is creating the normal force because you are standing on it. So it's the thing that's pushing up on you. Now the reading of the scale depends on how much you push down on the scale.
According to Newton's third law,
if the scale is pushing up on you with the force, you are going to exert an equal and opposite force on the scale. And based on that force that you exert on the scale, that will reflect the reading on the scale. So because the force that the scale exerts on you is equal in magnitude to the force that you exert on the scale, or your weight, by finding the normal force, we will find your weight
that the scale shows, or the reading on the scale.
So the goal now is to find the normal force. When the elevator is at rest, the net force is equal to 0. So the force normal minus the force of gravity is equal to 0. And so we can say the normal force equals the force of gravity. The force of gravity equals mg. Let's talk about when the elevator is accelerating upwards. The net force on the elevator is equal to the normal force minus the force of gravity, because gravity points downwards, and that is all equal to mass times acceleration. Force normal equals ma plus the force of gravity. And if you remember that 100-question quiz, you remember that the force of gravity is equal to mg. I'm going to rewrite this as the force of gravity plus ma. So when the elevator is not accelerating or at rest, the normal force equals the force of gravity. However, when the elevator has a positive acceleration, the normal force is actually greater than the force of gravity because you're adding on this extra ma. So if it was at rest or not accelerating, force normal equals force of gravity. But if you're accelerating upward, the normal force will actually increase. Same for time equals 3, the net force equals 0, so the normal force equals the force of gravity. Same for when the person is moving at a constant speed, the net force equals 0, so the normal force equals the force of gravity. When the person is slowing down, the net force on the person is equal to the normal force minus the force of gravity, and that is all equal to mass times a negative acceleration. So the normal force is equal to negative ma plus force of gravity. And so the normal force is actually equal to mg minus ma. This mg right here is the force of gravity, and I just flip-flopped their places. If mg is equal to the force of gravity, then you can see that the normal force is actually less than the force of gravity because we are taking away this extra ma. That is because the person has a negative acceleration. By finding the normal force in all these different scenarios, we have found the reading on the scale. So the scale thinks that the person weighs as much as the normal force. So whatever the normal force is in each scenario, that's what the scale thinks the person weighs. So when the elevator is at rest or moving at a constant speed, the scale would show your normal weight because the normal force is equal to the actual value of your weight. However, when the elevator has some sort of an acceleration, your weight shown on the scale will change. I'm going to more quickly go over a person that walks into an elevator on some high floor, so like on the 12th floor or something, and the elevator takes them down to the first floor. At the beginning and at the end, the person is at rest with zero acceleration. I'm still going to call upwards positive. They start from the top, and the person starts from rest and they accelerate downwards and they get up to a certain speed. Their speed is increasing, but their acceleration is actually in the negative direction. They have a negative acceleration even though they're speeding up, and that's because the net force is in the negative direction. They're speeding up in the negative direction. The force of gravity doesn't change. However, in order for the person to gain speed in the negative direction, there must be a net force in the negative direction, so the normal force must decrease and becomes less than the force of gravity. That is why when you're on an elevator and you start moving down, you feel kind of funny because the floor is pushing up on you less than your own weight. Alright, once the person gets up to a certain speed, they start moving at a constant speed. Their speed is constant. Their acceleration is equal to 0 because their speed is not changing and neither is their direction. So the normal force is equal to the force of gravity in magnitude because there's no acceleration. Then the person and the elevator must slow to a stop. So the speed is decreasing. Let's look at the forces first before we talk about acceleration. The elevator is moving in the downwards direction and it must slow down. So what that means is there must be a net force going upwards to make the elevator come to a stop since it's already moving downwards. So the force of gravity is here. However, the normal force must be greater than the force of gravity to create a net upwards force. That is what's going to make the person and the elevator slow down since they are already moving in the downwards direction. So because the net force is upwards, the acceleration is positive. And that seems kind of counterintuitive because you're slowing down, but because you are slowing down in the positive direction, the acceleration is positive. Net force is upwards, net force is positive, acceleration is positive.
Okay, number 29 from the best practice questions ever. I think you've done this in class, but I'm going to go over it as an example. A 50-kilogram student stands on a scale in an elevator. At the instant, the elevator has a downward acceleration of 1 meters per second squared and an upward velocity of 3 meters per second. The scale reads approximately blah. All right, let's attack it.
Okay, I'm going to draw a picture. I have a person standing inside an elevator. The elevator is originally moving upwards. I know the mass of the person is 50 kilograms. The initial velocity is 3 meters per second. I'm calling upwards positive. And the acceleration of the elevator, -1 meters per second squared. And I put a negative there because it says the acceleration is downwards and I called up positive, so downwards is negative. I'm going to draw a free body diagram of the person. So this is my person. There is the force of gravity downwards. And because the elevator was originally moving upwards, because the elevator was originally moving in the positive direction, and the acceleration is in the negative direction, I know that the net force must also be in the negative direction. And that means that the elevator is slowing down. So that means that the normal force is less than the force of gravity. This will allow the elevator to slow to a stop as it is moving upwards.
My target is the reading on the scale.
But really what I want to find is the normal force, because the person is standing on the scale, so the normal force by the scale on the person is actually going to be equal to the weight that the scale shows. So the normal force is our target. I have an acceleration and I have some forces and I have a mass. I think I'm going to use Newton's second law. Net force equals ma. What's interesting is that it doesn't matter what the value of the speed is at the beginning. We only care about the direction. So the net force is the force normal minus the force of gravity. Mass times acceleration, and because the acceleration is negative, I'm going to put a negative out in front. Sorry, I know you can't really see that. But when I rewrite this, I get the normal force equals the force of gravity. I added it to the other side, minus mass times acceleration. And the normal force is finally equal to mg minus ma. And if you want to be fancy, you can factor out an m. So you can see here that the effective acceleration is actually less than g, because if you were flying through the air in free fall, your acceleration would be 10 meters per second squared. However, in the elevator, they would never accelerate you at 10 meters per second squared. That would be quite the elevator ride. So I plug in some numbers, and I get that the normal force is equal to 50 kilograms, the mass, times g, which is 10 meters per second squared. And I'm taking away the acceleration, and I get 50 times 9, 450 newtons. So that is the normal force of the scale on the person. But the person is also pushing down on the scale with 450 newtons, and so that is what the scale will read.